In this video, we're going to talk about continuous functions. So in a couple lessons ago, we talked about continuous functions using the definition of continuity that dealt with just not being able to pick up your pencil when drawing a function. What we're going to do now is tie this idea into limits, since that's what we've been learning about. So by the end of this lesson, you should be able to answer the following little questions. How can limits help us to classify functions as continuous? And why is it useful to classify functions as continuous? And just as a reminder, by the end of Unit 1, you should be able to answer the following big question. How do we find the slope of a line using only one point? So as a warm-up, let's list the three types of discontinuities and sketch a picture of each. So throughout your lessons on limits, we've learned that we have three types of discontinuities. One of them is called removable, and a quick picture of this would be something like a hole with a point outside of the hole. We also have a jump discontinuity, which looks like one branch of a piecewise function and another branch that don't meet up in the same spot. You have a vertical gap there. And the third kind is an infinite discontinuity. And that occurs when we have a vertical asymptote and we have a function approaching a vertical asymptote, like that. Okay, so let's recall. In previous lessons, we said a function was continuous if it can be drawn without picking up your pencil. Now that we've learned about limits, we can use them to redefine continuity more precisely. So a function is continuous at a number a if all of the following conditions hold. Number 1, the limit of the function as x approaches a exists. Number 2, the function value at x equals a exists. And 3, the value of the limit of the function as x approaches a is equal to the function value at x equals a. Okay, so when we talk about continuity, instead of now just not picking up your pencil when drawing a function, we have these three conditions that deal with function values and limits. So that's how we're tying continuity into what we've been learning. Alright, so that's at a specific number. Now, a function is continuous on an interval if it is continuous at all the numbers contained in the interval. Okay, so it has to be continuous at every single little number inside an interval to be continuous on an interval. Okay, so this may sound kind of tedious, having to have the function value equal the limit at all these points, but it helps that many of the functions that we already know about are continuous. So let's look at the following example. So we can take for granted the following types of functions are continuous everywhere in their domains: polynomials, rational functions, exponential functions, logarithmic functions, root functions, trig functions, and inverse trig functions. So pretty much everything we know is already continuous. So let's quickly think about a function that isn't continuous in its domain. And the one that comes to mind first for me is the greatest integer function, or the floor function. So these are two names for the same function. So you may see it called either or. And we write this as either a double bracketed x or x with these little bottom brackets to represent the floor. Okay, so that's a function I can think about, and that's the function that looks kind of like this. So we've got these steps going on. Actually, yeah, it goes this way. Yeah, so this is probably one of those functions in school that you didn't talk about too much because it's kind of hard to think about. So It's one of those where you plug in a number and you round it down to the nearest integer. Actually, so that means it would go the other way, I think. Yeah. Okay, no, the way I drew it should be fine. Okay, so as an example, let's determine if the piecewise function sine of x as x is less than pi over 4 and cosine of x if x is greater than or equal to pi over 4 is continuous on all numbers, all real numbers. Alright, so since sine and cosine are both trig functions, we know that they're continuous by our previous example. So, if both of these branches are continuous, the only place where the function could possibly be discontinuous is at this place where the two branches split. So, the only place we could possibly have discontinuity is at x is equal to pi over 4. Thus, we will test to see if f of x is continuous at x is equal to pi over 4. Okay, so we're going to run through our three conditions of continuity. So first, we want to see that the limit of the function as x approaches a exists. So we're going to take the limit as x approaches pi over 4 of f of x. And the reason I'm only writing f of x here is because we have a piecewise function, so we actually need to decide what, well, we need to take the limit from both sides because it could be different here versus here. Okay, so let's maybe start with the left side. So the limit as x approaches pi over 4 from the left, we're going to use the sine of x branch. So for this limit, we can use direct substitution. And so I don't need to write limit anymore. We can say that that's the sine of pi over 4. And that's equal to root 2 over 2. Okay, now let's do the limit from the right. So the limit as x approaches pi over 4 from the right of f of x is equal to the limit as x approaches pi over 4 from the right of cosine of x. So this time we're going to use the cosine of x branch because of this inequality right here. So I can direct substitute. So this is cosine of pi over 4, which is root 2 over 2. So since the right hand and left hand limits are equal, the limit as x approaches pi over 4 of f of x exists. Okay, so that's the first condition. The second condition is that the function value at pi over 4 exists. So we want to test for f of pi over 4. And so if we're looking for the function value, we want to use this bottom branch here because this is the inequality that actually has equality with it. So this is going to be cosine of pi over 4. That's equal to root 2 over 2. So that definitely exists. Okay, and then finally for step 3, we just need that the limit is equal to the function value. So the limit as x approaches pi over 4 of f of x, we found in step 1 was equal to root 2 over 2, but that's also equal to the function value at pi over 4. So that's good. That third condition holds. So since all three conditions of continuity hold at x is equal to pi over 4, f of x is continuous on all real numbers. Okay, so the important thing to notice about that definition of continuity is that it does get a little tedious with having to write out the limit, showing that it exists, writing out the function value, but it's really important that we show each of those conditions of continuity, because really what we're doing here is writing a little baby proof. So we're having to prove beyond a reasonable doubt that this function is indeed continuous. So it is important that you write out all of the tedious details. Okay, so now we come to a theorem. So if two functions f and g are continuous, then any of the following combinations of f and g is also continuous. So what this theorem is allowing us to do is to combine functions that are continuous and still say that certain combinations are continuous. So we could add two functions, subtract two functions, multiply, divide. We could multiply by a constant, or we can compose two functions. And this is really handy, as we're going to see in the next example. So what this is going to allow us to do is to combine this theorem with the other example of all of the different functions that are continuous, and it's going to allow us to argue that a certain function, or that functions are continuous without actually having to test the definition. Okay, so for example, where is the function f of x is equal to ln excuse the coughing. Okay, sorry, I've been overseas for the past week and the air's been really dry, which is killing my allergies. Alright, so back to what we were saying. Where is the function f of x is equal to ln of x plus inverse tangent of x over x squared minus 1 continuous? Okay, so like I said, the idea here is to combine the function types with the combinations of functions and come up with continuity without having to go through the definition. So ln of x is continuous on its domain, and the domain of ln of x is 0 to infinity, not including 0. Tangent inverse of x is also continuous on its domain, which is all real numbers. So the sum of the two must be continuous where these two domains overlap, and they overlap at 0 to infinity. Now, x squared minus 1 is a polynomial, so it's also continuous everywhere, except where it equals 0, since it's in the denominator. And this equals 0 at x is equal to plus or minus 1. Alright, so since f of x is the quotient of two continuous functions, f of x is continuous everywhere on its domain, which we now know is 0 to 1, union with 1 to infinity. Okay, so just to recap, notice how we built this up. We started with the domains of all of the individual functions. We took the intersection of these domains to figure out like the sums, the differences, quotients, products, all of that good stuff. And with quotients, you kind of just have to be careful that the denominator, you exclude numbers where the denominator is 0. Okay, but once again, it's important that you write out all of the gory details to make sure that your logical flow starts from beginning to end. There's no gap in your logic for reasoning there. Okay, so we've talked about continuity. We've talked about how we can show functions are continuous in a couple of different ways. Now we're going to start with the idea of, well, what was the point of continuous functions? So continuous functions have a lot of applications that you're going to see throughout this course, some that are a little more maybe what you would think of an application, like a real-world application, but we also have lots of mathematical theoretical applications. So what we're going to talk about next is the first really big theorem in this class, which is called the intermediate value theorem. So this sounds really scary, but hopefully after I explain it, you'll be like, oh, that makes sense. How could that not be true? Okay, so the intermediate value theorem, or sometimes we shorten that to IVT. So suppose that a function f is continuous on the closed interval a to b, and let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in the open interval a to b such that f of c is equal to n. Okay, so that definition of the IVT, probably super confusing, isn't very intuitive, doesn't make too much sense. Let's translate that into plain English. If we choose a horizontal line, y is equal to n, between two particular y values, then the graph of f can't jump over the line if the function is continuous. So even the English translation might be a little confusing, so hopefully when you do this exploring the IVT activity and you see the picture, you'll be like, oh, that makes sense. Okay, so to do that, just scan this QR code here or use the link on Canvas to access the file. I'm not going to do that in this video though. We're just going to go to the next example. Okay, so example. And this is going to be a real-world application of the IVT so that you can see that so you can further see that, hey, even though we have this theorem with a big scary name, it's really kind of a common sense kind of idea. Okay, so on her 13th birthday, Jenny was 5 feet tall. On her 14th birthday, Jenny was 5 feet 2 inches tall. Use the IVT to explain why Jenny must have been 5 feet 1 inch tall at some time between her 13th and 14th birthdays. Okay, so we can think of height as a function of time. Since children don't skip heights and grow constantly, this function is continuous. So you're always constantly growing. You're never just like 4.5 feet tall and then suddenly the next day you're 5 feet tall. At some point you have to have grown all the places between there. So that kind of gives away the rest of the question, but we'll keep going. Since this function is continuous everywhere, it is certainly continuous between Jenny's birthdays. So 5 feet 1 inch is a height that is between Jenny's birthday heights. And she did grow during that year. Thus, by the IVT, at some point, Jenny was 5 feet 1 inch tall. So yeah, it's common sense, right? It seems like a waste of time to write out all of these sentences to explain that, well, between the time that she was 13 and 14, well, of course, if she was 5 feet and then 5 foot 2, of course at some point she had to be 5 foot 1. Like, the common sense, right? But it turns out, like, down the road, if you were going to mathematically prove the IVT, that's not necessarily an easy thing to do. So while this stuff might seem tedious, it's because while the IVT is intuitive and makes a lot of common sense, it's not very easy to prove. So it is important that we're using this logic and practicing explaining using mathematical logic. Okay, as another example, we're going to show that there is a solution to the equation 4x cubed minus 6x squared plus 3x minus 2 is equal to 0 between 1 and 2. So here we're going to do another baby proof, and this is another application of the IVT. So let f of x equal to 4x cubed minus 6x squared plus 3x minus 2. So notice what we've done is we've taken our equation and we've turned it into a function. So we just moved the, or changed the 0 to an f of x. we want to show that there is some number c between 1 and 2 such that f of c is equal to 0. First, we will show that all conditions of the IVT are satisfied since this function is a polynomial. It is continuous everywhere, so it is certainly continuous on the closed interval 1 to 2. So that's our first condition satisfied. We needed a continuous function on a closed interval. Now we check that 0 is between f of 1 and f of 2, and that f of 1 is not equal to f of 2. Okay, let's think really quick about what this means. So if 0 is between f of 1 and f of 2, that means we should be able to plug in 1 and plug in 2 to the function. One of the answers should be positive and one should be negative. So let's do that in the space below. So f of 1, we're going to plug in 1 to f of x, so we have 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2. That gives us 4 minus 6 plus 3 minus 2, which is negative 1, which is less than 0. Okay, so we have our negative number. Now let's try f of 2. So we have 4 times 2 cubed minus 6 times 2 squared plus 3 times 2 minus 2 is equal to 32 minus 24 plus 6 minus 2, and that is equal to 12, which is positive or greater than 0. So, since f of 1 is less than 0, sorry about that, and f of 2 is greater than 0, 0 is between f of 1 and f of 2, and f of 1 is not equal to f of 2. Okay, so we've shown all of the conditions of the IVT are met. So there exists a number c between 1 and 2 such that f of c is equal to 0. Thus, there is a solution to the equation between 1 and 2. Okay, so just to give you a little more detail on this, notice that this solution does not actually solve the equation. It just shows that there is a solution. So this is what we call an existence proof. So we're showing that a solution exists, but we don't actually solve and find what the solution is. So the reason this could be useful is sometimes you might have equations that are incredibly hard to solve, but maybe it's good to just know if you have a solution. So if you can test if you have a solution or not, then it might make it easier, or not easier to solve, but it would give you some guidance into, like, maybe you have a bunch of equations, you're deciding which ones to solve, and then you only want to solve ones that actually have solutions. So it's good to test if you if you certainly have a solution or not. So that's why an existence proof could be useful. Okay, last thing is just check your understanding. So make sure to answer this question in 2 to 3 sentences. And again, sorry for the coughing and sneezing. Dry air in Europe is very bad on the allergies. Anyway, that's the end of lesson 5.